Hey everyone, Hihu here from LeetCode. Imagine you're holding a balance scale. You keep placing numbers on both sides until become perfectly balanced. That's exactly what today's problem is asking us to find. Today we're solving LeetCode 724 find pivot index. It's an easy problem from the arrays and prefix sum section of the LeetCode 75 study plan. At first the solution looks pretty straightforward, but if we're not careful, we'll end up calculating the same values again and again. The good news is that one important value never changes. Once we recognize that, the entire solution becomes much simpler. But before jumping into the algorithm, let's first understand the problem. We're given an integer array called nums. Our goal is to find the pivot index. A pivot index is a position where the sum of all the elements on the left is equal to the sum of all the elements on the right. The current element itself is not included in either sum. If multiple pivot indices exist, we return the leftmost one. And if no pivot index exists, we simply return -1. Let's understand this with a couple of examples. Suppose our array is 1, 7, 3, 6, 5, 6. Let's check whether index 3 is the pivot. The element at index 3 is 6, so we completely ignore it while calculating the sums. Now look at the left side. 1 plus 7 plus 3 gives us 11. Next, look at the right side. 5 plus 6 also gives us 11. Since both sides are equal, index 3 is our pivot index. Now let's try another example. Suppose the array is 1, 3. Try checking every position. No matter which index we choose, the left sum and the right sum are never equal. So this array doesn't have a pivot index and the answer is -1. Now the obvious question is, how do we check every index efficiently? Let's begin with the most straightforward approach. The first idea is pretty straightforward. Let's pretend every index is the pivot and check whether it satisfies the condition. For each index, we'll calculate the sum of all the elements on the left, then we'll calculate the sum of all the elements on the right. If both sums are equal, we've found our answer. Otherwise, we move to the next index and repeat the same process. The logic is simple and it definitely works, but let's see how we'd actually implement it. We'll visit every index one by one. For each position, we treat it as our current pivot candidate. Now we calculate the left sum by looping from the beginning of the array up to the element just before the current index. Next, we calculate the right sum by looping from the element just after the current index until the end of the array. Once we have both sums, we simply compare them. If they're equal, we immediately return the current index because we found the pivot. If they aren't equal, we continue checking the remaining positions E. And if we finish scanning the entire array without finding a valid pivot, we return -1. The implementation is simple enough. Now let's verify it with a dry run. Let's use the same example. 1, 7, 3, 6, 5, 6. We start with index 0. The left side is empty, so its sum is 0. The right side contains every remaining element and the total is 27. The two sides aren't equal, so index 0 isn't our answer. Now move to index 1. The left sum becomes 1, while the right sum becomes 20, still not equal, and next we check index 2. The left sum is now 8 and the right sum is 17. Again, the two sides don't match I. Now we reach index 3. The left side contains 1, 7 and 3, giving us 11. The right side contains 5 and 6, which also gives us 11. Finally, both sides are balanced, so we return index 3. The algorithm works perfectly. But did you notice something? Every time we move to a new index, we calculate almost the same sums all over again. Let's analyze the complexity. Suppose the array contains n elements. We check every single index, so that's n possible pivot candidates. For every candidate, we calculate the left sum and the right sum from scratch. Each calculation can take almost n operations. That makes the total time complexity O of n squared. Now let's talk about space. We only use a few variables to store the left sum and the right sum. No extra arrays and no additional data structures are required. So the space complexity is O of 1. The space usage is already great. The real problem is the repeated work. We're calculating the same values again and again. Can we somehow reuse what we've already computed? Let's pause for a moment and think about what we're actually recalculating. For every index, we're computing the left sum and the right sum from scratch. But here's the question, does the total sum of the array ever change? No, no matter which index we're checking, the total sum always remains the same. So if we already know the total sum, do we really need to calculate the right side again? Not at all. Imagine you're standing at the current element. You already know the total sum of the array. You also know the sum of everything on the left. So what's left on the right? It's simply whatever remains after removing the left side and the current element from the total. In other words, the right sum is the total sum minus the left sum minus the current element. That's the breakthrough. Instead of calculating the right side every single time, we can derive it instantly. We only need two pieces of information throughout the entire journey: the total sum and the running left sum. This interview pattern is commonly known as prefix sum. But an easier way to remember it is this: keep a running left sum and derive everything else. So our algorithm becomes much simpler. Before we start checking any index, we calculate the total sum of the entire array just once. Then we begin moving through the array from left to right. At every position, we already know the left sum because we've been maintaining it as we move. Using the total sum and the left sum, we immediately derive the right sum. Now we compare the two sides. If they're equal, we've found our pivot index. If they aren't, we simply add the current element to the left sum and move to the next position. We repeat the same process until we either find the pivot or reach the end of the array. Now let's translate this idea into code. Now let's turn that idea into code. First, we calculate the total sum of the entire array. We'll only do this once because the total never changes. Next, we create a variable called left sum. Since there are no elements on the left of the first index, it starts at 0. Now we begin scanning the array from left to right. At every index, we derive the right sum instead of calculating it with another loop. We do that by subtracting the left sum and the current element from the total sum. Once we have both sums, we simply compare them. If they're equal, we found our pivot index, so we immediately return it. If they aren't equal, we add the current element to the left sum and continue to the next position. If we finish scanning the entire array without finding a pivot, we return -1. Let's walk through the same example one last time. Our array is 1, 7, 3, 6, 5, 6. Before we begin, we calculate the total sum. It comes out to 28. Now our left sum starts at 0 and we begin checking each index. At index 0, the current value is 1. The right sum becomes 28 minus 0 minus 1, which is 27. 0 and 27 aren't equal, so this isn't our pivot. Now we add 1 to the left sum and move forward. At index 1, the left sum is 1. The current value is 7, so the right sum becomes 20. Again, the two sides aren't equal. Now we add 7 to the left sum, making it 8. Next we reach index 2. The current value is 3 and the right sum becomes 17. Still not balanced. So we update the left sum to 11 and continue. Now we arrive at index 3. The current value is 6. The right sum becomes 11. Our left sum is also 11. Both sides are finally equal. So we found our pivot index. The answer is 3. Notice what happened. We never calculated the right side using another loop. We derived it instantly using information we already had. Let's analyze the complexity. We make one pass to calculate the total sum. Then we make one more pass to find the pivot index. Each pass visits every element exactly once. So the overall time complexity is O of n. Now let's talk about space. We only store the total sum, the running left sum, and a few temporary variables. We don't create any extra arrays or additional data structures. So the space complexity is O of 1. Let's quickly recap. The brute force solution recalculated the left sum and the right sum for every single index. The breakthrough came when we realized that the total sum never changes. Once we know the total sum and maintain a running left sum, the right sum can be derived instantly. That's the interview pattern to remember. Whenever a problem asks you to repeatedly calculate values on both sides, stop and ask yourself one question: can one side be derived from information I already know? If the answer is yes, you've probably found a much better solution. That's the core idea behind many prefix sum problems, and that's how we solve LeetCode 724, find pivot index. If this explanation helped you understand the idea, don't forget to like the video and subscribe to LeetCode. Thanks for watching. This is Hugh signing off. Keep practicing and I'll see you in the next one.